So now we are going to look into equations of motion. Now these are a set of equations which help us predict initial velocity, final velocity, what is the acceleration, what is the displacement or the distance covered, in how much time is the object covering a distance for one-dimensional motion. And we are going to start with one-dimensional motion with constant acceleration. So the first part that we are going to do is one-dimensional motion with a constant acceleration. And the first equation of motion comes from the very definition of acceleration, which goes like acceleration is defined as the rate of change of velocity. If we assume u to be the initial velocity, v to be the final velocity, and the time interval, let's call it t. So acceleration or the magnitude of acceleration would be given by v minus u upon t. So this would give us at is equal to v minus u, or v equals u plus at. And this is the first equation of motion, comes very simply from the definition of acceleration. Remember, this is for this case only, acceleration being constant. Okay, now let's move on to the next equation of motion, where we will utilize the definition of average velocity. Now, we know that average velocity is given by total displacement by total time taken. Total time taken is t, and let's call the total displacement with a variable s. This is the magnitude of displacement. Okay, we're going to find out the relation between displacement, time, and acceleration. So let's do that. The average velocity when acceleration is constant can be given by u plus v by 2. This is very, very important. You cannot write this for all the cases, okay? It's only possible when acceleration is constant, and we are going to look at it, okay? Why we can write average velocity as v plus u by 2. For now, just assume that this is correct, okay? Average velocity is for a one-dimensional motion having a constant acceleration can be given by v plus u by 2. Now this can also be written as s by t from this very equation, u plus v by 2. This is equal to s by t. Now let's say only the known quantities to us are initial velocity, acceleration is known, and time is known. We have to find out the distance. This is known, this is known, this is known. So how do we find it? See, this could have been the equation of motion if we knew the initial as well as final velocity. But here we don't know final velocity, so what we'll do is we'll try to convert this using the very first equation that we got, which was u plus at. We can write this equation as u plus, v can be written as u plus at upon 2 is equal to s upon t. And let's simplify this and let's see what we get. And that would be our second equation of motion. So you can cross multiply, and this becomes 2s on this side, and you get 2u into t plus a t square. And this becomes, you divide by 2 throughout, and you get ut here plus at square by 2. This is equal to s. This gives you s equals ut plus half at square. This is the very familiar equation of motion. This is our second equation of motion. How to get the third equation of motion? Very simple. You just eliminate time from equation 1 and equation 2. So you don't really need to remember the third equation of motion, okay? You remember any two equations of motion, that's more than sufficient to figure out, that's more than sufficient to find the answer to any given question. It's just that if you remember the third equation, you would be able to arrive at the answer faster. To get the third equation of motion, you eliminate time from equation 2 and 3. So this is your homework. You can try doing that. To get the third equation of motion, eliminate time from equation 1 and 2. If you do that, you're going to get the third equation of motion, which looks like this. V square minus u square is equal to 2as. This is your third equation of motion. Now, one very important thing to note, all these three equations are valid for constant acceleration case only. So what if acceleration is not constant? What if the motion is still one-dimensional, but acceleration also keeps on changing? It's either increasing or decreasing. It's varying as some function of time or it's varying as some function of distance. Whatever it is, it's not a constant. What then? Can we apply these three equations of motion then? No. Okay, we cannot apply these three equations of motion if acceleration is variable. So let's look at that now. What then? Then we shouldn't use the equations of motion. Then what we should use is the differential relation between acceleration, velocity, displacement. Okay, so just to recap, we define velocity, the instantaneous velocity, remember, as dx by dt. Or in some books, you would also find s written as, you would also find it written as ds by dt. Okay, s or x is your displacement. It's the magnitude of displacement. Here, x is displacement. Okay, so either of these formulae, it's the same. Okay, you can use this irrespective of whether acceleration is constant or not. Even if acceleration is variable, you are free to use this. You can use this. This will give you the answer. The other differential relation that you can use is acceleration is dv upon dt. So one relation is this, the other relation is this. And the third relation, which is basically derived from these two relations, is acceleration can also be written as v dv by dx. How come? Let's look at that. Okay. So we are going to derive the third relation from the second relation. Here's your hint. You can try it once on your own. Chain rule of differentiation. This can take you from step 2 or equation 2 to equation 3. You can try it out. So we already know from equation 2 that acceleration is given by dv upon dt. So what I'll do is I'll multiply dv by dt and divide it by the same quantity. It won't make any difference, right? If I multiply it by dx and divide it by dx. And then I'm going to pair these two things together and the remaining two things together. So I'll write dv by dx here multiplied by dx by dt. Now I think you can recognize this is nothing but velocity. And we've finally got what we needed, v dv by dx. This is written here and this velocity is written here. So we can say that acceleration can also be written as v dv by dx. Why did we need this? See, at times in question, you would be given acceleration as a function of time. When that is given to you, well, you can use the first two equations, okay? V equal to dx by dt and a equal to dv by dt. But in some cases, acceleration would be given as a function of x. What would you do then? So then this would come in handy, okay? This will give you the result faster. Okay, so it's good to remember all three relations. So when acceleration is variable, when acceleration is not a constant, then you use these three differential relations. V equal to dx by dt, A equals dv by dt, and A also equals to v dv by dx. So let's do a quick recap of what we just saw. We know constant or variable, doesn't matter if the acceleration is changing or the acceleration is constant, you can still use this, you can still use this always. Okay, let's take a look at what other information we can extract from these simple equations. And think about graphs. Let's look at the first one. V equals dx by dt. What does this tell us? It tells us that if you have the displacement time graph, if you have the displacement versus time graph, you can get velocity from that graph. How? Slope of displacement time graph gives velocity. This is one very important result to remember. Okay, what else can we extract from this? What other information can we extract? Let's look at this. When you know how velocity is changing with time, you can get the displacement from there. How? If you integrate velocity with respect to time and its definite integration from 0 to t, or whatever is the time interval from t1 to t2. If you integrate the velocity time graph between a given time interval, the result will give you the displacement. And this quantity gives area under the graph. So what did we learn again? We learned that area under velocity time graph gives displacement, right? Okay. So very important results. Please remember this. This will help you solve many, many problems. Let's now move on to the second equation, acceleration as dv by dt. From here, we can directly say that slope of velocity time graph gives acceleration. This is one information we can extract. The other information we can extract from this is area under acceleration time graph gives us something. What? It gives velocity. Please remember these four results, okay? Very, very important for solving questions. Once we are thorough with all the equations of motion, we can start solving problems now. So let's move on to questions.